Okay, so in the last section, we learned 3 different ways to get the equation of the least squares regression line. Right now, I want you guys to kind of shout out what those 3 ways were. Okay, if we were given data, we used the calculator. If we were given summary statistics, we used algebra. Remember the B equals R times SY over SX guy? Okay. And then if we were given the computer output, we just read it right off the computer output. Today we're going to talk about how well a regression line actually fits a set of data. Because as you've seen by now, some lines are better fits than others, depending on how strong the correlation is. A measure that actually tells us how well the line fits the data is r squared, which really is the correlation squared, okay? And this is called the coefficient of determination. What this actually measures is kind of hard to understand. We're going to think about it like this. If we had no idea what the relationship between x and y was, then our best prediction for y would always be the average y value. I'm always going to predict the average, okay? R squared measures how much better the LSRL is at making predictions than if we had just predicted y bar each time, the average y. Okay, how much better is the least squares regression line than just me predicting the average y every single time? The coefficient of determination, r squared, tells me what percent of the variation in y is accounted for by the least squares regression line of y on x. You need to memorize this, okay? If you do not memorize anything else in this class, you need to memorize this sentence. And I bolded the y and the x because you're not going to say y and x. You're going to tell me what those variables represent in context. You're going to talk about bunnies and manatees and boats and whatever horrible things we do problems about, okay? So for now, see, so serious. For now, write this down. We'll do some examples with it, but you really do need to memorize this sentence, and you will absolutely be tested on this at multiple points. Pause. Okay, hopefully we got all this written down. For the manatee problem, r squared was equal to 0.886. I can write this as a percentage, 88.6%, and I need to remember what x was. X was the number of boats in thousands, and y was the number of manatees killed. Killed. So I'm going to say 88.6% of the variation in y, which I'm not going to write y, I'm going to write the number of manatees killed, is accounted for by the least squares regression line. You may write LSRL. Yes, you may. By, the least squares regression line of y, the number of manatees killed, on x, on the number of boats. And you don't need to put units here because, as we're going to see later, changing units doesn't actually change r or r squared. So it's okay to leave it like this. 88.6% of the variation in the number of manatees killed is accounted for by the least squares regression line of the number of manatees killed on the number of powerboats. We can also measure how well the line fits the data by measuring the distances between y and y hat. Y is the actual y value of a point, and y hat is what the line predicts for that y value, or for that given x value. So these distances are called residuals. And the residual is the observed minus the predicted, or y minus y hat. An acronym that a student came up with for memorizing this was ROMP. Residual is observed minus predicted. Examining these residuals can tell us how well our regression line fits the data. And the sum of the residuals of a least squares regression line is always 0. This should make you think back to the hair lab. Remember your residual pieces of string added up to 0? Same things happen here when we're dealing with bivariate data. So let's calculate the residual for the manatee data in the year 1985. Now I need to get this data. Here it is. Okay, so in 1985, my actual data point was 585,000 boats, and 33 manatees. So if I go back here, 585, 33 was the point. And my residual is going to be y minus y hat, observed minus predicted. The observed value for y was 33, minus, how would I get the predicted y value? Well, I have my least squares regression line, and I have it written down from when we did this problem. It's negative 41.43 plus 0.125x. And so to get y hat, I need something to plug in for x. Well, I'm going to plug in this x value. Okay, so this is going to be negative 41.43 plus 0.125 times 585. And that gives me 31.695. 31.695, which is what my regression line predicts. So 31.695, which if I subtract gives me a residual of 1.305. What that means is that in 1985, I don't know, here's my regression line, and here is the point for that year. Okay, so on the x-axis, here is 585 boats. 585 boats or 585,000 boats makes a prediction that's right here, but the actual value is a little bit above that. So positive residuals mean that the point falls above the line. Negative residuals would mean that the point falls below the line. The actual value is less than what I predicted. And we should see a good mix of positive and negative residuals because remember the residuals sum to 0. I can make a graph of residuals. This is called a residual plot. A residual plot is a scatter plot of the residual values versus the explanatory variable x. So it's going to have x on the x-axis and residuals on the y-axis. Some computer outputs, instead of putting x on the x-axis, put y hat on the x-axis. We will not do that. It's kind of weird, but it doesn't change the overall shape, so you don't need to worry about that too much, okay? So every now and then, instead of seeing x on the x-axis, you'll see y hat on the x-axis, but we can handle that if that kind of example comes up. This is sort of an example of a residual plot. So again, here on the x-axis is just whatever the x variable was. In this case, you probably can't see it, but it says temperature. And then on the y-axis are the values of the residuals. This right here is very important. If the linear relationship is appropriate, if my linear model, my LSRL, is a good fit, then my residual plot should have no pattern. I should see points scattered irregularly all over this horizontal line, which is a residual of 0. Okay, so here, points above the line have a positive residual, points below the line have a negative residual, and I'm looking for no pattern, okay? And I see no pattern here. This shows me that the original linear model was a good fit. What a residual plot does is it basically takes a scatter plot and rotates it so that the LSRL is horizontal. Then points above have positive residuals, points below have negative residuals. You can create a residual plot in your graphing calculator. So we're going to do this again with the manatee data. So let's go back to that data and make sure everybody has it in their calculator. So get out your calculator and check that, again, we don't care about year, but that the powerboat registrations are in list 1 and the manatees killed are in list 2. Pause if we need to enter this data. Okay, so to create a residual plot, what you are going to do is, first of all, you need to calculate the equation of the least squares regression line. The LSRL needs to be showing on your home screen in order for your calculator to actually do the residuals. So I'm going to go to Stat. Do you remember where we go to find the LSRL? Over to Calc. And then I don't choose the first lin reg, I choose the second one, which is option 8. So I'm going to go to option 8, lin reg, hit enter, and now the equation of the least squares regression line is showing on my home screen. Okay, now I need to go back into my list editor. So I'm going to hit stat edit, and I need to go all the way over list 3, list 4, list 5, list 6. You may have more than this. You're going to go to your first blank list. Okay, when you go into uncharted territory, for me it's after list 6. Up here it's just blank. Okay, and what we're going to do is create a list in which our calculator is going to find the residuals. And you have to call it resid, R-E-S-I-D. So for me, the alpha key is already on. I'm not sure why that is, but if it's not, hit alpha and this A will be blinking, okay? And you're gonna literally type R-E-S-I-D. And so there's the R, it's above the multiplication button. E is above the sign button. I guess I hit alpha again. E. Okay, I'm having to hit alpha each time. I think if you hit second alpha, it locks the alpha. S is above the natural log button. You're probably done already. I is above the x squared button. And D is above the x to the negative 1 button. Resid, okay? Once I've typed in resid, hit enter. And like magic, your calculator is going to calculate the residual for each x value. So for each x value, it's calculating the actual y value minus the predicted y value for that given x value. Okay? Now I'm a little scared, so I'm going to quit. Okay? And we are going to create a residual plot. So I'm going to go to second y equals, okay, and go into my first plot. Make sure it's still turned on. I want it to be a scatter plot, so that's still good. I still want my X list to be list 1, but instead of list 2 being my Y list, I want my Y list to be these residuals, okay? So you can either type resid again, or now that you've created a residual list, it'll be in your lists menu. So you can hit second stat, and down at the very bottom should be resid. So I'm going to type in, or I'm going to choose it that way. You can type it if that makes you uncomfortable. But this is what your screen should look like. It should be on. It should be a scatter plot of list 1 and resid. Let's quit. And I'm going to zoom 9. And here's my residual plot. Okay, I see this horizontal line. Those represent residuals of 0. And I have some above and some below. And I see no pattern here. And so that means that my regression line was a good fit for this manatee data. We'll talk about what types of patterns you can expect to see in just a second. But I don't see any pattern here. It looks like it has a correlation of 0, which in this case is a good thing because that means that the linear model was a good fit. Okay. So a few notes about residuals. Like I said, the residual plot should not have any obvious patterns. Some patterns that you should be on the lookout for are a smile pattern, which is going to look like this. Yes, some residuals are above and some residuals are below, but I have a pattern to them. What this means is that my original regression model was actually curved. So it would be like that. Do you see how that kind of scatter plot could lead to this kind of residual plot? If I take this guy and rotate it about 45 degrees, I would get this picture, more or less. Just like a smile, I do not want to see a frown. That means the same thing, okay? It means I had an original curving to my scatter plot. And then the last one that you should be on the lookout for is a fan. You won't see these as often, but a fan means that at first I had small residuals, and then as the x values increase, those residuals get bigger and bigger and bigger. That means my data fanned out, which meant initially it was really strong and then it got weaker. The fan could go in the other direction. I could start with these big residuals and then get smaller and smaller in. Those are all indicators of data that is not actually linear. And then the residuals themselves should be small in size, okay? But that's a relative term, so that's not something you can really check for. The main thing we're looking for is a lack of pattern. A few things to remember about correlation. It makes no difference which variable you designate as x and which you designate as y. If you flip x and y, you will get the same correlation. That doesn't mean that it's okay to just flip x and y. If I have a clear explanatory and a clear response, then the explanatory should be x and the response should be y. But if you do flip them, you will get the same correlation. Because correlation calculations rely on z-scores, R will not change if I change units of measurement. So if I change x from inches to centimeters and I change y from miles to kilometers, I would still get the same correlation. We know this, but a positive correlation indicates a positive relationship and a negative correlation indicates a negative relationship. R always falls between -1 and 1. So if somebody tells you that the correlation between your SAT scores and your GPA in college is 1.08, then they don't know anything about statistics and you should not listen to what they say. Correlation requires both variables to be quantitative. So similarly, if someone tells you that there is a strong correlation between hair color and GPA, again, they don't know what they're talking about because hair color is not quantitative. Okay, I cannot make a scatter plot with hair color on the x-axis and GPA on the y-axis. That is ridiculous. Correlation only measures the strength of a linear relationship. We cannot use it to describe a nonlinear relationship regardless of how strong it is. So if I have this beautiful, perfect curve, correlation is not going to tell me anything useful. I can calculate it, but it's not going to mean anything. The correlation is not resistant, similarly to mean and standard deviation. In fact, correlation is calculated from means and standard deviations. So if I have outliers, the correlation is going to be affected. And correlation alone is not enough to summarize bivariate data. We need to also be looking at residual plots. We need to be looking at the equation of the least squares regression line. We need to be examining the scatter plot and looking for outliers. The correlation is not enough. Okay, that's it for today's lesson. Here is homework number 3. We learned some pretty complicated calculator stuff today, and those tutorials are on the website as well. So the calculator tutorials that I've added for this section are making a scatter plot and finding the equation of the least squares regression line and making residual plots. So there are 3 more calculator tutorials on the website now. Hopefully some of you have seen those.